Good, okay. And Yunus now should be able to start sharing.
Yeah.
So what I'm showing you here is data from Cook County, Illinois, which is the seat of Chicago, Illinois, broken down by neighborhood and by the fraction of people in each neighborhood that is non-Hispanic Black, that's Hispanic, or non-Hispanic White. And when you look at the city, you can see clearly it's segregated, meaning that these three races of people are not evenly distributed throughout the county. And understanding what causes the segregation and its effects is important because, especially when thinking about Black and segregation, it is correlated with minority communities experiencing greater exposure to pollution or use of police force, like police violence, and unequal access to education. So to address these questions, try to find out what is causing the segregation and its negative effects, we've developed a statistical physics inspired approach that quantifies the segregation for the first time in a functional form using curves like this. That'll be like energy curves. And then we use these curves to forecast how these neighborhoods are likely to evolve into the future. And these forecasts additionally are useful because they tell you they can help inform decisions about where to build new houses or new schools or allocate social services. And so the first part is going to be focused on quantifying this social behavior underlying this data. And to do that, I want to just show you first some simulations of 3 different cities simulated from a Schelling model, which is a standard agent-based model used in demography. And in this case, you see a whole bunch of red and blue people segregating from each other in these 3 different cities. Now, demographers don't usually have access to individual addresses of people, but they do know the compositions on each of these little neighborhoods. So here, the redder blocks have more red people. And if you look at this data, you might say that they look similarly segregated. And indeed, the segregation index, which is the traditional way, standard quantitative demographic way to measure how separate the red and blue people are, it's the same segregation index for all 3 different cities. So they would say they're all behaving the exact same way. But if you look more closely, if you look at what's the probability of observing a given fraction of blue people in any given neighborhood, you'll see that all 3 cities are actually very different from each other. This one, the neighborhoods are very happy being either all red or all blue, while this one, there's something asymmetric, and the red and blue people are not exactly the same. So inspired by this, we wanted to develop a metric that would remember all of this information instead of reducing it to a single index. And to do so, we need to do a functional measure of the segregation. But looking at the distributions themselves is not enough because there's other things going on. I'll show you about that later. We need to develop a metric that is invariant to the sample size. So if you're looking at blocks that have 15 or 200 people, it should still be able to extract the same segregation behavior. It should be invariant if you compare 2 cities that have more blue people or less blue people, and it should have some sort of interpretation so people know what's going on. So inspired by that, with those goals in mind, what we do is we fit these probability distributions to something of a Boltzmann distribution over here. And this is inspired by some density functional theory approaches we've developed in other works. But right now, I'll just give you the intuition that this acts as the probability of observing a given fraction of people in a given block size S. S is the number of people in a block, is some combinatorial term, which is like an entropy term, which counts the number of ways you can organize all your red and blue agents within your block. And an function on n in this exponent up here. This h is meant to suggest it's like a Hamiltonian, but we're going to call it just a headache because we don't really have any conserved quantities here yet. So we can take these 3 probability distributions and perform this transformation, fit them to this form right here, and we get 3 headache functions like this. And for now, when we read this, I want you to just interpret this as if it's an energy landscape, where this is some sort of statistical penalty for being observed at integrated values here, being 50-50 is less likely because it's got, this is like an energy hill, and the segregated values are more likely. And so now, why do we do this? What does this transformation give us? And to understand that, I want to look at, to get some intuition, let's look at a few different cities. So on this top row are 3 random simulations where the red and the blue people can't tell the difference between each other. There should be no segregation at all, and they're technically just binomial distributions. And the columns are for cities of different compositions. So these are for 30% blue, this is a city with half blue, and this is a city that's got 70% blue people. The bottom row is the same overall compositions, but now with some sort of segregated behavior. And right away, you'll say, if you look at these segregated functions, it's hard to say that the underlying interactions between the red and blue people are the same. You just have more blue people in some cities than others. But when you do our transformation into this headache function, you will notice a few things. First, the random collapse onto being straight lines. In the cities, the blue line is for a city with 30% blue people, which means that there is a constant penalty for becoming bluer because there's less blue people than red people, while the 70% has a different slope. It slopes down, meaning there's a constant reward for a neighborhood to become bluer. But when you look at the segregated blocks, you'll also see that the shape of this hill is the same between all 3 of these different cities. The only difference is that they're tilted. And I could show you the plot to convince you better of that, or you can just trust me that
Yunus, looks like your sound and image is frozen. We don't see you moving. Maybe you have bandwidth problem, like maybe your internet froze or something. I think we should all just wait for a while if connection of Yunus unfreezes. I'm not sure he receives this message. But for the rest of the audience, I guess just try to stay and wait until Yunus manages to reconnect, hopefully. Yeah, it's a bit probably, okay, Yunus disconnected. Okay, fine, so the bad things happen on the internet. I guess, my guess is that his internet connection was probably too weak and it probably just dropped out, connection dropped. And so he disconnected. I don't see him among the list of participants. Okay, so basically, we just wait until when, if he manages to reconnect. But meanwhile, well, I have to just relax and have a good time because Vinkat already dropped out from the list of participants, so you cannot ask him questions. If anybody wants to say something funny, you feel free to. Can you call him? I don't know. I mean, I have no contact information of Yunus. They could be probably possible to email him, but I do not have email address. Maybe organizers can do, or technical support people can contact him, but I don't have any information to do that.
Yeah, Venkat, Victor, I'm sending him an email. That's the only one way I can reach out to him.
Yeah, that's right. That's right. Okay. Yeah, in fact, that's right. I was also on this email, in fact. Okay, so Ram, right? You will send him. Yeah, you'll send him email, right? In fact, I was on this email. That's right. Okay. So while we're waiting, if anybody has something like, to say something to other people, something to share, or thoughts or comments or whatever, you have time to do that. You can fill in this, the gap in performance if you want to. Okay, Yunus reconnected. Okay, great.
Oh, I'm so sorry. The power went out and the router went out. But,
power? Okay, power went out.
Sorry.
Okay, go ahead.
But I'll try to catch up. Okay, so I'm not sure how much you missed either, but the idea is that probability distributions, when we fit them to Boltzmann-like distributions, we can get some sort of energy function describing the underlying interaction.
Make sure you share the screen. Make sure you share your slides because slides are not shared yet.
Thank you. Thank you. There we go. Okay. So
we stopped.
exactly.
We saw this curve that these two like this and one like this. We saw this. That's roughly speaking where
Okay,
we.
good.
That's where you stopped more or less. Yeah. Mm-hmm.
Okay. So the idea is we want to extract these interactions between these segregated subgroups from data. And so now I'm going to talk about how we do that to census data. So again, I'm showing you Chicago, Illinois, and the problem is every single one of these neighborhoods has a different total number of people. These blocks are just drawn by the American census. So some might only have 1 person, some might have 200 people. So in order to get our energy-like function, our H function describing the segregation, we have to do some sort of maximum likelihood approach, which is shown here. But you can just trust me that I do that right, and we get curves that look like this. And you're going to see a whole bunch of curves that curve up and then back down. I'll help you, I'll show you the differences between them in a little bit. But right now you can just see that Cook County, Illinois, when you're looking at white, non-white segregation, is segregated. But before we get into looking at individual counties and comparing different parts of America, I want to first look at what is the general trend for segregation between these different races across the entire United States. So here we have the energy function for every single county in America as a function of the fraction. I'm going to break into 2 different parts. One has a potential-like term, which just tells you about that slope that I told you about earlier. And that just characterizes how many white or black people live in different parts. And a global frustration function, we're going to call this F, function of frustration, that characterizes the underlying social interactions. So just for context, because I know there's people from all over today, this is America, and this is the fraction of people in every single one of these counties. There's about 3,000 counties in America that is white. So the white people tend to live in the north. And if we apply this analysis, the nationwide typical white, non-white segregation curve looks like this. And there's a potential surface, a spatial potential field that says that white people tend to live in these places with lower potential around here and tend to avoid places down here in the south. You could do the same thing when looking at black versus non-black populations. Black persons in America are concentrated in these East Coast cities and down here in the south. That'll be important later. You get, again, a black, non-black segregation curve, or you can do Hispanic. And Hispanic, black, and white account for about 90% of the population, so this gets most of the people. And here, Hispanic people tend to concentrate down here, and here's your Hispanic, non-Hispanic segregation curve. Now, the first question we might want to ask is, depending on our categorization of people, Hispanic, non-Hispanic compared to white, non-white, compared to black, non-black, which experiences the greatest level of segregation? And we find that the black curve right here for black, non-black segregation is the highest, while white is the second highest, and Hispanic, non-Hispanic has the least amount of segregation. And this is something that's roughly known in the segregation literature. So that's good that it agrees with what the demographers have been saying so far. The other thing we might want to ask is, how has segregation changed over time? So now we're going to plot from the year 1990 to 2010, the white, non-white segregation. And again, if you look, you go from green to orange to purple, you see that the segregation has decreased over time. And that's also something that people in the field for this type of segregation typically agree on, although I'm glad we had an income inequality talk before this, because there's different types of segregation that are arising these days. I won't get into that. But I will get into looking a little bit more detail at the black, non-black segregation. So black, non-black segregation has also decreased over time. But as you've noticed, all these curves kind of look all the same. So I'm going to look at more detail as to differences between these different energy curves. So what I'm going to do is I'm going to fit it with this dotted line. I'm just going to find the average of these three, and I'm going to subtract this dotted line away from these three curves so we can see more detail the differences. So it's the same data, except I've subtracted the mean, and you have the year 1990, 2000, and 2010. And since the 1990 is more of a hill, it goes up and down. It's more segregated, roughly, but your eye is probably being caught by these wiggles in the middle. This is all I forgot to say at the beginning, these are all tentative results, and I'm still figuring some of this out. I think these wiggles in the middle are due to overfitting and the fact that there's not a lot of data here. So I'm going to ignore those. I'm going to just plot the left and the right-hand side where most of the data lies, either the neighborhoods that are all non-Black or the neighborhoods that are almost all Black. And one of the discussions that is big in the literature is about how American neighborhoods are gentrifying. So as an aside, there is, in many neighborhoods in America, historically Black neighborhoods have had white persons who on average make much more money, move into the neighborhoods, drive up prices, and then the Black neighborhoods are, they lose a lot of their social and cultural history, and then they disperse because they can no longer afford to live there. But the thing is, people have pointed, that would happen over here at the neighborhoods that are all Black. While over here, these are the neighborhoods that are all non-Black. These are the neighborhoods in America that are mostly all white. And so if we compare how has segregation changed over time for Black populations, the curves that change their slope the most are here at the ones where it's become easier for Black persons to move into neighborhoods that are mostly non-Black. And that's due to a bit of a rising middle-class Black population. And less strong is the signal here where these lines all have about the same-ish slope that would be correlated with gentrification. So this is already helping to settle some of the debate in the literature about how important is gentrification in the changing demographics of America. But, and so just to check, let's look at the counties that are known for gentrification, so Baltimore, Los Angeles, and Washington. If we look at all of those, from 1990, it was hard for a Black person, it was less likely for other people to move into an all-Black neighborhood. But then by the time you get to 2010, it became much easier for a non-Black person to move into a all-Black neighborhood. And instead of saying easier, I should say more probable. And same for Los Angeles and same for Washington, DC. So far we've been looking at assuming there's one type of segregation across the entire nation. What if we allow there to be two types of segregation? How would that naturally split the United States? So it becomes this complicated computational problem that I don't have the answer for yet. But what I do have is a clustering algorithm that approaches that answer, but I won't go into this algorithm just yet. I'll just show you some of the results. It says, what if we allow there to be, in Alaska and Hawaii, I still have not figured out how to put Alaska and Hawaii down here because they don't actually belong here. So sorry if you're from Alaska or Hawaii, but your data is involved, it's just not plotted. What I've done here is I've separated America into blue counties and red counties. And the blue counties have this blue extra frustration, and the red counties have this red extra frustration. I'm looking at white, non-white segregation in the year 2000. And what you'll notice, especially from the United States, is that in these red areas, that's where the non-white population is going to be largely Black. So this is in the South, or in the East Coast cities, or even up here in Seattle. While in all these blue cities, blue counties, it's where the non-white population is largely Hispanic. And the difference largely comes from this difference in slope over here, where in the red counties, it is much harder for a non-white person to move into a neighborhood that's all white, much less likely. While for the blue counties, it's more likely for a non-white person to move into an all-white neighborhood. And so already we're being able to characterize much more than could have been done with just a simple segregation index, which is what's previously been done in the literature. So, and here's the text about that. So then we can also ask what happens if we add more clusters and look for more behaviors. So here I'm showing you the quality of our fit. It's the log likelihood of the fit as we allow there to be more and more frustration functions. And of course it should go up since you're adding parameters to our model, but it tells you about how far we should go. This dotted line is if you just allow there to be as many clusters as you want. And by doing that, we can then watch how segregation, look for even more emerging patterns arising from within here. And one thing you notice, like, if you're in the States, is that there's a south and then there's deep south effect that happens pretty quickly. That's pretty interesting. So I said I could measure, quantify segregation, but the other thing that these functions are useful for is forecasting how neighborhoods are likely to change into the future, which has typically not been done before. Normally, demographic forecasts just tell you how many millions of people are going to move from one country to the next. They don't tell you how your neighborhood's demographics is likely to change into the future. So to do that, it's hard to visualize the entirety of America. So what I'm going to do is just take a subset of the American block groups. And block groups are groups of blocks as a census definition. In order to watch how neighborhoods change over time, you have to go to a coarser scale, but I'm going to continue to just call them neighborhoods. I've chosen all these neighborhoods that are from counties that are between 50% and 70% white, and that have between 700 and 1,300 people. And so again, you can see it looks pretty segregated. It certainly doesn't look like a Gaussian distribution or binomial distribution. And so what I want to do, though, is I want to take subsets of these. I want to look at the neighborhoods that started in the year 2000 as being all non-white or half white or all white. And so I'm just copying those three distributions here and ask what happened to those neighborhoods in the year 2010. So you'll see two trends arise. One is that all of these move towards the left, and I'll get to that in a minute, meaning they move towards less white, but that's just, there's white population decreased by 6%. But the other thing you'll notice is that the segregated neighborhoods tended to stay segregated, but the integrated neighborhoods were much more free to change their composition over that time period. And that's exactly what our H function says. When you get out of the segregated neighborhoods, it's much more easy to change your composition once you've integrated a little bit. And so we should maybe be able to capture that with our functions. So to do that, I'm going to consider another little agent-based toy model for intuition. Let's say we have this neighborhood of 25 people. We choose a random person. So we chose this random red person and removed him. And then we choose to replace that person with either a blue person or a red person. We do that with this probability, which is 1 plus e to the delta h, which is a little familiar. And what that does is it penalizes replacing this red person in a way that will increase the H function for this neighborhood, while it will reward it if it decreases the H function. And there's a similar rule for blue to red as well. If we do this, we'll get the exact equal steady state probability distribution that gives rise to this headache function. So it seems like a good candidate for trying to forecast dynamics of how these neighborhoods will change. If we do that, we can build transition matrices that look like this. And what I want you to notice, the way to read this, first off, is that each row corresponds to an initial population of white people. So this first row here is that there are no white people in that neighborhood. This is if there's 1,000 white people in that neighborhood. What you'll see right away is that the non-white neighborhoods stay non-white and the all-white neighborhoods stay all-white, while the integrated neighborhoods move around more. But we have a problem in that 10-year time period, the Hispanic population and other population, this was largely driven by Asian growth in America, grew a lot. That's what these bars are showing you, which led to a percentage decrease in the white population by 5.4%. So what we can do is add in one more little term here. So it's the same for every single neighborhood. It's just a change in potential that will drive down the population so that at the end of a certain time, we'll have the desired future fraction of white people. If we do that, we can change our transition matrix and it will push all these neighborhoods down to fewer white people. And so we can forecast, given the initial composition of any neighborhood, what's its likely future composition 10 years later. And so this is what we've observed, and this is what we get if we choose the time snippet of that transition matrix that best overlaps these two distributions. And they seem to agree in my opinion. So to recap, what we do is we take this density data, and from that we extract functions that describe the way the different subcomponents of these populations are interacting with each other. And we use that to extract trends that both are well accepted in the literature and also more nuanced ones that are under debate. And then we can use those descriptions to forecast how, for the first time on a neighborhood scale, normally they can only make predictions at most on a county level scale, how a neighborhood is going to be impacted by population changes.
Okay, it's time to wrap up. You know.
Okay, last thing. Thank you.
Mm-hmm.
The last thing I didn't get to tell you about is that it's easy, it's somewhat trivial, just computationally hard to extend this to multiple groups. So here I'm showing you the H function if we simultaneously look at what's the probability a neighborhood is a given composition, Black, white, and Hispanic. So here you can see the least likely occurrence here is where it's most equal Black, white, and Hispanic. So then you can simultaneously look at interactions with Black, white, and Hispanic people. So with that, I want to thank the organizers, and I would like to have take there's time for any questions. Thank you for your time.
Okay, thank you very much, Yunus. Being on time also. Okay, so any questions?
Yes.
We have like a couple of minutes till the beginning of next session. I don't see anything on chat, and nobody raised hand, but you can still ask if you like to. Just unmute your microphone if you want to and ask a question. Veronica, you raised hand, did you?
Hello?
Yep. Yes. Please go ahead and yeah, unmute and turn on your whatever video better, and just go ahead and ask.
Okay, thank you. I have thank you for this talk. It was really interesting, and I have a question because, as far as I understand, you have data about neighborhood, but you cannot have data about persons. But then the assumption about decisions is about persons. So I was wondering whether the scale, how much does it matter, and how much is it included?
Yeah, statistically, all we're doing is describing what's the probability of a neighborhood having a given composition. But what we'd like to do is we can posit one dynamic model whereby we say individuals move from this neighborhood to that neighborhood by looking at how likely the neighborhoods are to change their compositions in that way. That would be interesting for demographers, at least, to understand what's driving these segregation behaviors. For instance, there's debate whether it's due to things like income inequality. So Black people make much less money than other populations, so they tend to live in the same neighborhoods, maybe just because the housing is cheaper there. Or is it due to racist housing policies, which there's a long legacy of that here in the United States? Or is it maybe just due to the fact that people have shared cultures and they want to live next to each other? So helping to disentangle those would be useful, and I think we need a little bit more about the individual decisions to understand that. And but really what we just are saying is the dynamics of the neighborhood compositions. We derive this from density functional theory, so the idea is by simplifying, by just looking at density, which we only have density data anyway, what's the most you can say from just looking at this density data?
Okay. Okay, so I think we're pretty much exactly on time. So I think we should probably close this session now and hand it over to the chair of the next session, Michael McCullough. Okay, so now Michael, the floor is yours, and you can start next session. Thank you everybody for presenting and participating.
Okay,